Okay, folks, the last couple of lectures have run a little bit long, as I'm sure you've noticed. So I'm just doing a couple of short ones today. I want to close out our discussion of LC with just a little bit of a recap of the stuff that we've talked about in terms of HPLC instrumentation. Um, and then in the second part, I just want to kind of introduce some of the things that we're going to be thinking about differently in terms of GC than LC. And then we'll wait until essentially next week in our next lecture to get into some of the deeper inner workings, mechanisms, theory of GC that are kind of unique from LC. So let's do a little recap on HPLC instrumentation. So here's a little diagram that sort of framed our conversation. It's two mobile phases going into one pump. That pump feeding an injection valve. And then flow from the injection valve going to a column. And finally, a detector. And I just want to remind us all of what we've seen in these different categories. So let's start with the pump. So we've seen the operation of an isocratic pump. This is a pump that can deliver just one mobile phase, and so we can't get gradient elution. But we've also seen binary pumps. Which is essentially two isocratic pumps side by side, right? So the ability to send two mobile phases and in various ratios so that we can achieve gradient elution. And then we've seen also the design of this thing called a quaternary pump. And a quaternary pump is just a four-way proportioning valve attached in front of an isocratic pump. And so this allows us to produce even more complex gradients of multiple solvents. I'm not sure if we mentioned this when we were talking about it, but one of the big uses of these things is trying to figure out what method you want to work with, right? If you don't know what mobile phase you want, it's nice to have a selection of four already hooked up to your pump so you can run through many different methods and kind of figure out what you're doing there. Okay, so we're going, by the way, I should say, we're going input to output in our discussion this morning. That's not how we talked about them, actually. I think we went here, here, then we jumped over here, then we spent the last little bit of time talking about what happens in here. But this morning we're going to go input to output. So after the pump, we get the injector. And the big thing we talked about here was the design and operation of the classic 6-port injector. One thing I may have mentioned is that in modern chromatography systems, you have this auto sampler system integrated with one of these 6-port injectors. You don't always actually see the 6-port injector yourself. It's often computer controlled or mechanically controlled out of sight, but so it's often integrated into an auto sampler. Auto sampler, there we go. But the main point here is that an injection port like the 6-port injector, it allows introduction, or I guess a better word is injection, of course, introduction of sample into the high pressure system without breaking that high pressure, right? Without having to come down to atmospheric pressure in order to put your atmospheric pressure sample into the high pressure liquid flow. Okay, the thing we spent a great deal of time talking about recently is the column, and what's happening in the column. So the column is where we define our mode of chromatography. Of course, it's not just the stationary phase in the column, so I'm going to say along with our mobile phase selection, the column, of course, it's contained stationary phase. Define the mode, what we're calling the mode of chromatography. So let's look at some of the modes that we've looked at. Modes of liquid chromatography. So we started by talking about adsorption, right? This is a fairly simple system to put together because it just requires essentially silica particles. You shove sand into a column and you have an adsorption column. It's the original, it's the OG of liquid chromatography. It's what Mikhail Svet was essentially inventing, I guess like 120 years ago now. But the real challenge, and I haven't said this enough, I have said it enough, but I've said a lot, that it's about essentially having retention that is just too strong, right? So, and this comes down to uh, a bunch of factors. It comes down to the strength of the intermolecular forces on those hydroxyls on the surface of a silica particle. It comes down to just the number of them there are. They're packed really densely right on the surface. We said when we talked about bonded phases that you have essentially up to 4 times as many functional groups retaining things in adsorption than you do in a bonded phase method, because the yield in a bonded phase method might be something like 25%, right? So retention is just too strong, and this is what makes adsorption not a great technique. But sticking with the concept of interactions that happen right at the surface of the particle and not with these fancy bonded phases, um, actually, that's probably not an accurate statement to say. You use bonded phase chemistry to produce ion exchange columns, so I don't want to mislead anybody here. But it does remain kind of a direct, a strong intermolecular action, kind of like what you have here. Exchange. So that's IEC, ion exchange chromatography. And this is basically the idea of formal charge based binding to the stationary phase. And we saw several different varieties of this. There was strong and weak. There was the ability to retain anions, the ability to retain cations. And so we gave them these fancy acronyms: strong anion exchange, weak anion exchange, strong cation exchange, or weak cation exchange. I'll remind you the difference between strong and weak here is that strong exchangers, strong stationary phases for strong anion exchange, they always have their charge, and so the only thing you can do is compete for binding with the mobile phase. But weak anion and weak cation exchangers, they have this acid-base functionality on the stationary phase, so you can turn binding on and off by affecting the pH, right? By switching the pH, you can tweak the binding capacity of the stationary phase, which is a pretty unique property that you get in ion exchange, but you do not see in virtually any other technique. Okay, we also saw size exclusion chromatography, which has some other names. It goes by gel permeation chromatography or gel filtration chromatography. This is strictly a size-based separation. strictly a size-based separation, and it is governed by the diffusion of your different analytes into stationary phase pores. Into the pores of the stationary phase. And so naturally smaller molecules can diffuse into more and deeper into each pore. Um, and so they are retained longer. Um, the retention order here is from large to small. So small things come off last. And these are resolved across a range that we call total exclusion. So from things that are too big to get into any pores to total inclusion. That is things that are small enough to get into all the pores. So anything small enough won't be resolved from other things that are small enough to get into all the pores. Anything too big to go into all the pores won't be resolved from other things that are too big to go into any of the pores. And the last thing I think we'll say here is that there is a pretty, sorry if I'm running off the edge of the screen here, or off the edge of the paper, at least there's a limited peak capacity. And that is the factor that makes this a fairly low resolution technique. We're not looking to resolve one Dalton in mass between two molecules because it doesn't change their size significantly, and we can't resolve size quite as well as we think we might like to. I think the article we looked at said something like a peak capacity of 13 or so. So whatever your resolving range is, break it into 13 parts. That's how you know how well it can resolve particles. Okay, and the last thing we were talking about was bonded phase modes. So to be clear, bonded phase is not a mode itself, but it's a technique that we used to invent basically three different modes of chromatography. The first, normal phase, or NPLC. So it just gives the same retention order as adsorption. But so why do it, right? If you already have adsorption techniques, it's because it has dramatically reduced retention factors, lowercase k's. So we've said a bunch of times, chromatography stops being useful once your k's hit about 15. So by reducing the number of functional groups, reducing the strength of the intermolecular forces on those functional groups, but remaining a polar functional group as a stationary phase binding motif, allows you to reduce the overall K and get back into kind of that useful retention region. Okay, the second was reversed phase, or RPLC. This is the big one, guys. This one is maybe 75% of all HPLC applications. It gives the opposite retention order. I've always thought that it's a little bit ironic that the technique that everybody uses is not the one that's called normal, right? The normal phase is maybe something like 10% of applications. The overwhelming majority are these ones that are reversed, and it's called reversed despite being by far the most common thing because it gives opposite retention order. And at this point, forgive me if you can hear my daughter in the background. She is having a great time today. Okay, we tend to look at mobile phases here that are composed of H2O and a miscible organic, something like acetonitrile. Also, methanol is used a lot here. This is a big advantage because these are fairly expensive. Acetonitrile can get kind of expensive. It has a market, kind of like gas. The prices fluctuate. It can get kind of expensive, but generally speaking, these are cheaper molecules than the organic solvents we use in normal phase. So that's a benefit there. And the stationary phases, so these are mobile phase compositions. Stationary phases tend to be saturated. It's not exclusively. We saw the phenyl stationary phase, which was not a saturated hydrocarbon, but the majority of the work here is with columns like C4, C8, C18, and then there are some exotic phases that you can find. Okay, and the last one that we saw was uh, hydrophilic interaction chromatography, or HILIC. So let's start by saying that this is it's a relatively new technology. I'm not talking about in the last year or two, but I am talking about in the last decade or two. And considering some of this stuff is 50, 60, 70 years old, that's relatively new. So it's a relatively new technology. Um, and the kind of the hallmark, the way I like to think about this is that it's normal phase, um, stationary phases plus reverse phase, RPLC, mobile phases. And this results in a thin water layer that plays a role in the stationary phase. Okay, those were our modes. Last thing we're going to talk about are detectors. What I'm not going to do is I'm not going to go through a complete rehashing of every detector we looked at. I want to show you remind you of the big categorizing factors that help us think about detectors in different ways. So the final thing in our workflow is detectors. And we had two ways of categorizing these. The first was universal versus selective. So let's remind ourselves what this was. Universal is going to give a signal for most or all analytes. It does this because the signal is typically based on a bulk property of the solution that's going through the detector, not necessarily a property of any specific analyte, but a bulk property, things like refractive index of that solution, for refractive index detectors, electrical conductivity of that solution for things like conductivity detectors, or thermal conductivity of that solution for thermal conductivity detectors. Um, the downside to this, so it kind of sounds good to have peaks for everything. I would argue it's not great to have peaks for everything because you rarely care about absolutely everything in your sample. But the other downside is that by looking at everything using these bulk properties of solution, this typically gives, um, these detectors typically have higher LODs and poorer sensitivity. So sometimes this terminology gets confusing if you're not used to thinking about limit detection. Higher is bad, right? Higher LODs, these are bad. Okay, so then the other side of this coin, universal versus selective. So like a selective detector gives signal, so I guess we'll say it responds to a specific property of the analyte molecules. So my favorite example here is like a fluorescence detector. Every molecule doesn't fluoresce. Some do naturally fluoresce, and you can look at those and ignore everything else. You can selectively make individual molecules fluoresce by tagging them with fluorescent tags, and then you're selectively looking at those. Even if there's another analyte there, you don't see it, right? So it gives you the chance to hone in on exactly what you're interested in measuring. As a result, these typically give better or lower LODs and higher sensitivities. And I guess we did put a little caveat in. We said mass spec can kind of do both of these. You can make an ion out of just about anything under the right conditions, so it's universal. But you get a specific property of each analyte when you measure it in the mass spectrometer. Its mass to charge ratio, so it can kind of do both. And I'm going to say because it's rad. It's a cool technique. It's a cool technology. All right, the other categorizing methodology we used for detectors was mass sensitive versus concentration sensitive. So in a mass sensitive detector, the signal, sorry if you can hear my daughter asking for water out there, the signal is proportional to the total number of molecules that will pass through the detector, right, in the solution that sees the detector. And because mass-sensitive detectors are proportional to the total number of molecules, it's appropriate for LODs should be given as quantities that relate the amount of stuff you have, right? So that should be as a mass. So our limit of detection is, 10 femtograms or whatever. Or it should be as moles. We can detect 5 picomoles or whatever. But it should not be as concentration. It shouldn't be mgs per mil. It shouldn't be molar, but people still do that. And it becomes confusing because someone will tell you they get extremely low. So mass spec is an example of this, right? Mass spec is a mass sensitive detection method because the mass spec itself is going to catch all the ions it possibly can, and then it's going to concentrate them and measure the number of ions that made it into the mass spectrometer. If someone gives you a mass spec method and says we have limits of detection of, you know, 10 femtomolar, right? That's a concentration, molar, 10 femtomolar, but they don't tell you that it took them 150 mils of sample introduced into their mass spec to get that concentration. You don't really get the real picture of what it took. So I guess what I'll say is don't be fooled. Don't be tricked by people reporting. Don't be tricked by people reporting as concentration because they do it all the time. Okay, so then the second is concentration sensitive detection, where our signal is proportional to the concentration of our analyte. And the LODs here should be given as some kind of concentration. So that's molar or variations of molar, right? Micromolar, nanomolar, picomolar. Or it's often given in something like mgs per mil, mass per volume. It's not uncommon to see detection methods here listed as ppm or ppb or ppt, which again is a concentration, right? Because it's amount parts per another amount of parts, right? So it's a ratio like any concentration should be. All right, friends, this was the input to output review of LC instrumentation. Took a little longer than I expected, but we're going to move on now to a very brief introduction to GC before next week when we really hit GC a lot harder.